and then I'm talking to myself for 5 minutes, and then we fall behind.
Times and
Projectile motion.
concerts are synonymous, but for this DJ, his good times came to an end from what we hope will be his last stage dive. The object here is to run, dive, and be caught by the concert goers. Well, he ran, he dove, but no one got around to catching him. Fortunately, he lost only consciousness. The rest of him remained relatively intact.
So that's one example of projectile motion.
Inches from the bottom of your screen. That line is where envy stops.
Here's the second one.
You're thinking about throwing someone in the pool. Make sure there's one there.
That's the third example. She's not very impact happy, is she? Fourth example. All right, guys, projectile motion is everywhere. Projectile ever got is projectile motion. This arrow is projectile motion. Bombs are projectile motion. And whenever the doctors are operating on you, when they pull out the internal organs and squeeze them really tight, trajectory of those organs is also projectile motion. Speaking of projectile motion,
I was trying to let you know that I had to go to Angleton to get.
Here's a slight mind twister.
By the time I got back, is
all right, guys. You have to.
Almost time for me to start class. In fact, I'm in class right now.
You have to mute yourselves. All right, so here's a slight mind twister. Notice that he's holding she's holding a rifle, exact same height. Okay, so as soon as she pulls the trigger, he's going to drop the bullet. So the question is, which bullet is going to land first? One which is dropped, or the other one which is fired from the same height? What do you guys think? Just put it in the chat if you want to. All right, so I see one. Connor says both of them at the same time. Jonathan says drop one is going to land first. All right, so what else? All right, so that's as far as we got. 2 comments. Okay, the comment. Okay, so most of you guys say the drop bullet will land first. All right, it's the common sense. Okay, so every single person who says something, give yourself 5 points. So far, so good. Common sense will argue that it's going to land first. Why? I mean, there's a lot of force behind this bullet. So much force, in fact, that if you were to stand in front of it, it can literally kill you. All right, so this bullet is just going to travel like half a mile, maybe a mile. And this, on the other hand, is going to fall unimpeded. So the argument is, and you will agree with that, this bullet is going to land first. All right, so that's the argument that most people would present. Is that a valid argument? Because I see someone, Connor says, both of them will actually reach the ground at the same time. So which one is the best argument? Which one is the right argument? Forget the best argument. The best argument may be the wrong argument. I give you a really damn good argument. All right, that's a very commonsensical argument. Okay, so this was a slight mind twister. Okay, this is not really that complicated. So common sense versus whatever physics is going to come up with. The next one that I'm going to give you is a mind twister. Imagine that you are an animal lover. I mean, some people like cats, some people like dogs, some people are monkey lovers. Imagine that you love monkeys to an extent that you're volunteering at a zoo. Okay, so your boss comes up to you one day and says, "Hey, the monkey that you're in charge of has escaped." You want to know how's that even possible? So they got a story for you. All right, so here's your monkey. Going through a projectile motion in this escape.
Yeah, it's kind of like that. Sierra Mist. Taste one shockingly refreshing lemon lime.
All right, so I want you to go capture the monkey. What do you need? All right, guys, this is false advertisement. Sierra Mist is not going to work. Monkey's not going to go for it. You're thinking, how about bananas? I'm thinking, not. Bananas are not worth your freedom, so that's not going to happen.
Tranquilizer.
Yeah, you got it, man. You guys are quick on the draw. Tranquilizing gun. Okay, so both of you guys, those of you guys who said that, give yourselves 2 points for that one. Tranquilizing gun. Okay, it just so happens this dude doesn't have a tranquilizing gun. Damn it! Instead, they got a tranquilizing cannon. Oh my god! So you go out and find the monkey, and the monkey is hanging from a tree, and you're about half a football field away from the monkey. All right, half a football field. It's 50 yards, guys. That's 50 yards. Okay. Now, when you fire the cannonball, it's not going to go so fast that you're going to kill the monkey. That's not the purpose. It's going to go fast enough to stun the monkey if you can hit the monkey. Okay, and here's another catch. As soon as you fire the cannonball, it's going to make a loud booming sound, right? So the monkey's going to get scared. He's going to release his grip at the moment you fire the cannonball. So if the monkey gets scared and releases his grip at the moment you fire the cannonball, where would you aim? Above the monkey, at the monkey, or down below the monkey? All right, just put down your, whatever it is that you're thinking, just put it in the chat. Above, at, below. I just want to see where we are. I want to see what the consensus is. So far, below. You guys are aiming below the monkey. Below the monkey. Oh my, most of you guys below. All right, give yourself 5 points, too many variables. I don't care about the variables. Just commit to it. Okay, above, one person, Sarah says above. Okay, we got enough responses, so we'll test it. So majority of you say below the monkey. Majority says below the monkey, below the monkey, below the monkey. How far below, guys? Are you thinking, let me aim right at the ball so I can hit him right in between the eyes? Is that what you guys are thinking? All right, so now we're ready to answer the first one. All right, first one was a leading mind twister. Common sense says that one which is dropped should reach the ground sooner. So you got 2 bullets, the drop bullet should reach the ground sooner. Physics says not really. Physics says no, that's not at all what should happen. According to physics, what should happen is both of them should reach the ground at the same time. I'm thinking, how could it be? I'm thinking it's free fall, guys. Ignoring friction, what's the only force acting? Gravity. What does gravity do? Gravity makes everything fall at the same rate. Remember, regardless of their weights, under the influence of gravity, the feather and the hammer would be falling at the same rate. This week, we're adding on to it. We will say, regardless of how fast the bullet may be moving horizontally, it's still going to fall under the influence of gravity. All right, that's known as projectile motion. So projectile motion, in essence, is the same as free fall. Remember, free fall is the motion under the influence of gravity and gravity only. This is also the motion under the influence of gravity and gravity only. It doesn't matter how fast this bullet is going to get fired from the gun. It doesn't matter that this is going to travel half a mile, 1 mile, 2 miles. I don't know. It doesn't matter. Everything is still going to fall at the same rate of acceleration. All right, so the projectile motion along the y direction, along the vertical direction, is the same as free fall. In fact, Mythbusters conducted this little experiment. All right, so this is one of my favorite shows.
Is needed to match the solar light.
Used to be.
The drop versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Victory for physics. Or is it a victory for physics? Let's go back.
The drop zone.
Okay, guys, common sense says the drop bullet is going to land
I
first.
think this might be
And the drop bullet lands first. What do you mean by victory for physics?
the shot we've been looking for.
According to physics, they were supposed to land at the same time. Did they land at the same time?
That's negating air resistance, so the shot bullet was much faster. So the air resistance, I'm assuming, I don't really know, in the downward direction, because v squared should be higher in theory.
Okay, so Sarah, I'm going to give you 5 points for commenting. Okay, did they land at the same time? The answer to that question is no, obviously. Okay, so according to physics, they were supposed to, and when they did the experiment, the drop bullet ends up landing first. But then again, now we have to look at it a little bit more carefully. The drop bullet landed before the fire bullet, right? By, what is it, 39 milliseconds? What's the 39 milliseconds? It's about 40,000th of a second. That's 400th of a second. Okay, so the time difference is very small. And that's known as experimental error. Okay, guys, there is no perfect experiment in real life. There's nothing about life which is perfect. Take a look at this here, 2020. All right, so crap happens all over the place. Mythbusters spent literally days trying to perfect this experiment. They tried their best to minimize the error, and that's the best that they could come up with. All right, and there's a reason why the fire bullet ends up landing second. Okay, not the first, but the second, because there's a bit of time spent inside the barrel, so it doesn't stop falling immediately. On top of that, the fire bullet, what does it do? It spins. So what does it matter? Well, it spins. It's just like a football. When a quarterback throws a football, what happens? It spins. Why does it matter? It matters because the ball generates a lift when it's spinning. Same thing happens to the bullet. So it's falling, but there's a bit of an air friction. It's just making it generates a lift. So this thing is not falling as fast as the other bullet does. It's remarkable that it still lands almost at the same time. So well within experimental error, and this is the proof of the pudding. Yeah, they do land at the same time. So this is a victory for physics. So what do we know from this experiment? We know from this experiment that projectile motion is the same as free fall. All right, last week we knew that the weight didn't matter, the size didn't matter, the mass didn't matter. Everything was falling at the same rate. And what do we know this week? We also know that the horizontal motion doesn't matter. I don't care that you're speeding up or going at a constant speed along the horizontal direction. Everything is still going to fall at the same rate. All right, so pick out the best answer and place your answers in the chat. Okay, very good. I see a lot of C's. Give yourself 5 points. That's right on. Okay, so simple enough experiment. That is in free fall. Yellow is in projectile motion. Critically, notice that they follow the same distances at the same time. All right, simulation that I did is not working on PowerPoint. All right, projectile motion. It's going to have two components along the y direction, along the x direction. Along the y direction is speeding up under the influence of gravity. So this is free fall. Along the x direction, ignoring the effects of air friction. There's no reason for this object to speed up or slow down. So notice that it keeps moving at a constant speed. How do we know that it's moving at a constant speed? The distance between adjacent points is the same. So it's moving at constant speed along the x direction. All right, so let's move on to a mathematical model at this point. So chapter number 3, we're studying motion in 2D, so 2D-dimensional motion. The topics that we're going to look at. We'll spend 80% of our time in projectile motion. So projectile motion is going to be 2D-dimensional motion. You end up getting this arc that's known as a parabola. So it represents the trajectory of motion of that ball that you're looking at. It's got an initial velocity. It's got an initial angle. They're not going to be the initial angle. So it's going to move along the x direction. That's known as the range. It's just moving up and down along the y direction. All right, so this represents the height. Yeah, it's going to take a certain amount of time for it to move along the x direction. And I want you to notice that it's going to take the same time along the y direction while it's going up and down. So this time is the same as that time. So the times are identical. All right, so this is a velocity vector. So it's going to have two components. It's going to have a component along the x direction and the y direction. And there's going to be a final speed. Its final velocity is going to have two components along the x and the y directions. And if you know the components along the x and the y directions, you can actually construct a velocity vector. I will show you how. But for now, let's make a transition to the full projectile motion from the sideways projectile motion. Okay, I want to make this transition because mathematically it's easier. Okay, so it's a step in between. So the students usually make the adjustments easier if I step into this. So sideways projectile motion simply means that motion is going to start at the peak of its arc that you're looking at. There's going to be a horizontal speed. It's not going to be a vertical speed. So only in the y direction, the speed is going to be 0. So as the object is moving horizontally, it's just going to fall under the influence of gravity. All right, so sideways projectile motion. Okay, so what I'm going to do is I'm going to make a transition to the sideways projectile motion, okay, from free fall first. So these are complete free fall equations. The first one is going to locate the object for you at a given point in time. The second one is going to tell you how fast it's moving at that time. The third one is going to tell you how fast it's moving at that point. But what I'm going to do, I'm turning it into a sideways projectile motion. I'll get rid of the initial speeds along the y direction. So we will have 3 reduced formulas. All right, so you know the vertical location for a given time, you know how fast it's moving in the vertical direction at that time. And if you know the vertical position, you know how fast it's moving along the vertical direction. Along the x direction, believe it or not, the motion is going to be predictable because once again, there's going to be uniform acceleration along the x direction, except there's no reason for the object to speed up or slow down. So that acceleration is going to be 0. So it's going to be a uniform 0 acceleration. What that means is the acceleration terms will drop out. As a result, these are going to be reduced to 3 equations. All right, so final speed is going to be the same as the initial speed. The squares of the final and the initial speeds are the same, so the last equation is redundant. So everything is reduced to 5 formulas. Okay, so play with those 5 formulas. So 3 formulas from free fall. These are the reduced formulas. There's no initial speed along the y direction. Along the x direction, there's no acceleration, so the acceleration is going to be 0 along the x direction. All right, so free fall, projectile motion. Notice that they travel the same distances within the same time periods in the y direction. Along the x direction, this thing moves horizontally, in this case at a given speed. So that's one of them is projectile motion, the other one is in free fall. All right, so we're focusing on
If you're in Mexico and you can't decide
sideways projectile motion.
between the bullfight or cliff diving, we've got the perfect town for you.
Here's one example of sideways projectile motion. Here's the second one. All right, so the sideways projectile motion is going to start on top of the peak of that parabolic trajectory. There's going to be an initial speed along the x direction. Case in point is the Fireplug. All right, so it's being fired from this height. There's going to be a horizontal speed for lengths. All right, so this is the projectile motion that we're looking at. All right, so now that we got a mathematical model and we have a bit of an understanding of what should happen with Fireplug and the drop bullet, let's do it mathematically and check to see if the mathematical model that we have actually works. All right, so we will fire a bullet horizontally, so it's going to get projected along the horizontal direction. It's going to fall under the influence of gravity. All right, so a bunch of stuff is given. So this is the amount of time it's going to take for it to fall. And within the same time period, it's going to move horizontally in this direction. Okay, so let's focus on what's given. We know the initial speed of the bullet is going to be 2,500 miles. We also know that it's being projected or fired from a height of 6 feet above the ground. Okay, and we also know that ignoring the effects of air friction, gravity is the only force acting on it. All right, so it's going to be roughly about 10 meters per second squared. So what do we want? Okay, so we want to know the amount of time it's going to take for it to fall. And we also want to know how far it's going to travel within that time period. That's it. All right, so we'll check to see what the range of this bullet is. All right, so now that we listed everything, before we move forward, let's do the conversions to proper units. All right, so miles per hour to meters per second. And then feet to meters. So we got our numbers. All right, so we're ready to go. Okay, so now let's get 5 formulas that we had. So 3 from free fall, 2 from horizontal motion. So we got 5 formulas. Let me just label them so it makes it easier to discuss stuff. Okay, so T is what we're looking for. Okay, so, and up to and including part A, these are the letters available to us. All right, so these are the letters that are available to us. All right, so, okay, so these are the letters that are available to us. Okay, this is what you want. All right, so which means that we have to focus on those formulas that have T in them. All right, so what do we have? The first one has T in it, second one has T in it, fourth one has T in it. So which one do we get to use? Let's start off with the fourth one. Okay, so we got T, it's got T in it. It's got the initial speed, that's promising. It doesn't, also it has X in it. And we don't have an expression for X as yet, so it's got 2 unknowns. Because it's got 2 unknowns, 1 equation, 2 unknowns, we're good, we can't use that. If you look at the second one, once again, it's got T in it. We know what G is, but we don't know what the final speed is on the Y direction. So this is no good. So now focus on the first one. All right, it's got T in it, which is good. We got an expression for G, so that's also good. And we also have an expression for the letter Y, so that's also good. So it's got 1 unknown, so that's the one that we will use. All right, so we'll just pick that one. So that's the one that makes sense to use. All right, so sub for T. So I move things around like they're my unknowns on the left-hand side. So get rid of 2 and get rid of G. Square root both sides. We're done. Okay, we're done. All right, so that's the final equation to which we will substitute the numbers. All right, so we got the letters. Okay, so it's a wiggly 10, which means it's an approximate 10. So it's going to give you 6/10 of a second. So the bullet is going to take about 6/10 of a second to reach the ground. That's what it means. All right, so everything is going to be done with in a fraction of a second. The next question is, how far will the bullet travel within 6/10 of a second? So X is what you want. X is right here. There's only one formula that has X in it. This is the only one. Okay, so this one is a no-brainer. And so X is what you're looking for. You know the initial speed, which is this. You know the time, which is 6/10 of a second. So that's the formula that we get to use. Okay, so they plug the numbers in metric units, and it's going to give you the number in terms of meters. No good. We have to convert it to something that we can relate to. Miles is going to work better because it's a fast traveling bullet. Then we do a conversion to miles, and it's going to give you about 4/10 of a mile. Okay, it's almost half a mile, guys. So this bullet is going to land within 6/10 of a second, almost half a mile away. All right, so it makes sense. So the next question is, how about the bullet just drop? All right, so when you drop a bullet, how long will that take? All right, so we know conceptually that it should take the same time. It should take 6/10 of a second. But how do you do it mathematically? Guys, it's the same as free fall. So you're limited to only using these 3 formulas. And the only one that you cannot use the last one because it doesn't have T in it. You can try this one. You don't know the final speed. So the only one that you can use is this one because you know the height, no G, sum for T, which you already did in part A of the question. All right, so it's the same as part A of the question. So the fire bullet is going to take 6/10 of a second. Drop bullet is also going to take 6/10 of a second. So they will land at the same time. All right, so the mathematics, the model that we came up with works. It agrees with our observations. All right, so put down your responses in the chat. Okay, good, guys. If one of them takes 4 seconds, the other one is also going to take 4 seconds, right? The fire bullet and drop bullets will land at the same time. The one which is projected at 30 meters per second, if it takes 4 seconds for it to land, 60 meters per second is also going to take 4 seconds to land. Beautiful. Give yourselves 5 points. All right, so now let's make a transition from projectile motion to impact.
Right.
All right, so projectile motion is going to end with impact. Impact could be soft, which means that you will have a really large acceleration time. Or it could be hard, which means that your impact time is going to be fairly small. Your acceleration time is going to be small.
Television cameras are on hand to capture a death-defying stunt. Daredevil Jean-Louis Arola is about to attempt a dangerous mid-air plunge into the frigid waters of the English Channel. The risky maneuver calls for him to drop from the plane as it speeds above the surface of the water. Jean-Louis carefully climbs out and secures himself to the belly of the fuselage. The aircraft approaches the drop zone.
Okay, so we got some problems here. Let's say 30 feet drop, and he's a stuntman, which means that this guy actually does this sort of stuff for movies. And when they shoot these scenes, and today most of they do special effects, but if they have to get a stuntman to do something like that, they would get a physicist to do the computations for it, just to make sure that no one is getting hurt. All right, so from the looks of it, someone missed the point. I think they end up focusing too much of the distance fallen and less on the fact that the airplane was moving horizontally. And this doesn't look too good at this point. Okay, so the question is, what were the impact that this guy underwent? Question number one, is that survivable? If it is, what's the damage? Okay, so let's do an analysis on this one. So what do we know? We know that the airplane was going at 80 miles per hour. And then when this guy jumped, he fell about 30 feet. That's it. That's all the information that you have. From that information, can you figure out whether or not the impact is survivable? Okay, guys, your test question next week is going to be like this. All right, so you're not going to have a lot of details. I'm going to give you the essentials. And out of that, you should be able to do a complete analysis. And how it is done is something that I will show you first. First thing I'm going to do, I'm going to step you through it so that you can see how the work is done. Next thing is, this is calc-based physics, which means that your problem-solving skills have to be a little bit more sophisticated and sort of problem-solving that we're using so far. All right, so what do we know? 80 miles per hour horizontally. That's how fast the airplane is moving. So when he jumps, he's already moving in the same direction at the same speed. Horizontal speed is going to remain the same all the way down. There's no reason for him to go any faster or slower. All right, once he's airborne. And while he's moving horizontally at speed, he's going to fall 30 feet. I'm going to drive this out. So he's moving 80 miles per hour horizontally as he's dropping in the y direction for about 30 feet under the influence of gravity. All right, and then he's going to land in water. All right, so let's figure out the vertical speed component of the final speed, y component. Figure out the horizontal component of the final speed. If you know the vertical and the horizontal components, now you can construct the final speed itself. All right, so figure out the total speed. And there's a bit of a shallow angle here, so figure out the angle of impact. And that's it. Okay, so that's our starting point. So figure out the final speed, and then we'll do an impact analysis. So I listed everything. Before I move forward, I just want to make sure that everything is in the correct form, because you don't want any confusions. You want to make sure that your numbers are in the proper form before you move forward, because this thing is going to be involved. So miles per hour to meters, second, feet to meters. Okay, guys, we've done the conversions quite a few times. At this point, it's a good time. This is chapter number 3. I know how to do the conversions. I haven't seen the first test yet, but at this point, I have to assume that you do know how to do it. All right, so moving forward, what do we do? All right, so without showing the work, I do the conversions because I know how to do them, and you should too. So miles per hour in terms of meters per second, feet in terms of meters. Okay, we're good. The next point is just find the y component of the motion, speed, final speed. Immediately, you notice that there are 2 formulas that you can use, 2 and 3. Both of them have the y component of the final speed. Now you've got to make a decision. Do you pick the second one or the third one? Well, try to pick the second one. Immediately, you notice that you don't have time, so it's out of the question. So through elimination, trial and error, you know that the third one is the only one you can use. Okay, because you know the distance found. Okay, cool. Get rid of the square by taking the square root. That's as far as this goes. All right, so the numbers in terms of the metric units. And then obviously the number in terms of something that you can understand. So this is roughly about 30 miles per hour. So this guy, when he hit the water horizontally, the vertical speed was 30 miles per hour. Now, what is the horizontal speed? Horizontal speed doesn't change. Ignoring the effects of air friction, there's not going to be any change in speed. Okay, guys, horizontally, speed does not change. Right, that's it. Okay, so there's no reason for him to go any slower or faster. So horizontal speed is going to be 80 miles per hour. So that's the x component of the speed. Okay, now let's make a transition to full projectile motion.
Presenting
It's metal.
Medieval Knievel.
So what angle maximizes the range?
Thank you.
Thank you very much.
You're brilliant.
Please.
Not everything can be as good as the original, but Diet Dr. Pepper is.
Obviously, it's not the right angle. So what angle maximizes the range? Okay, guys, let me ask you a completely different question. What angle maximizes the range? Oh, okay, I see 45 degrees. How do you know? How do you know that the 45 degrees maximize the range? All right, so those are you guys who say 45 degrees, maximize the range. How do you know that? All right, do you know that because most of you guys, for most of you guys, it's book knowledge. I don't really rely on book knowledge that much because this is something that you can learn through experiment. I knew that when I was a kid. The reason why I knew when I was a kid is because I grew up in Turkey, and I know baseball is huge in the United States. Don't care much for baseball. I find it really boring. And maybe part of the reason is because I don't understand the game. And so I grew up playing soccer, and when I was growing up, we didn't have a lot of parental supervision, so it was fun. So you would play for hours and then drink water. And then in order to make it competitive, we used to do pissing contests. That's a real thing. All right, so for a trial and error, you discover that, hey, 45 degrees is going to maximize the range. So you don't have to look it up. You can actually experiment. For opting is, though, forget 45 degrees. It's going to maximize the range, but look at 75 degrees. Look at height you can gain at 75 degrees. Stuff that you can do with it at 75 degrees. So imagine that you're at a baseball park, been there a couple of times, all right? The game is boring enough, so most people drink, including myself. So if you're drinking, obviously you got to go piss. And then when you go to the bathroom, there are lines. So what I'm about to say is going to make perfect sense to you if you're tipsy and drunk. Okay, you're in a hurry, you have to go, except you cannot hold it much longer. And you're right behind this guy, and you're thinking to yourself, I wonder if I could piss over this guy's head. And you know, it might be possible at 75 degrees, all right? All right, so if you want to try something like this, my recommendation is practice. This is something that you have to practice at home. All right, get your little sister or brother, check to see if you can piss over somebody's head. The last thing you want to do is try to piss over somebody's head while you're tipsy in a park. All right, because you're going to end up hitting someone in the back of the head, and nothing is going to piss someone off more than getting pissed upon. All right, so remember, 75 degrees is the way to go, and 45 degrees is going to maximize the range.
Was killed and more than 100 hurt yesterday when a United Airlines jet traveling from Japan to Hawaii suddenly took a big dive. 11 of those injured are still in the hospital tonight. Correspondent Bob Orr reports.
All right, so this one.
Passengers and
All right, so this one was your observation in the beginning of this semester.
flight attendants who were in
Airplane
the process of
flying into air turbulence.
dinner were slammed headfirst into overhead luggage bins. I went through the ceiling, said this battered passenger. I was panicked, said another. People were crying everywhere. The jetliner with 100 injured, a dozen seriously, turned back to Tokyo. Dazed and heavily bandaged passengers walked off the plane. Others were carried. Paramedics worked feverishly, but without success, to revive one Japanese woman who died of head injuries. While turbulence is a common occurrence, deaths and serious injuries.
So when the airplane flew into air turbulence, a bunch of passengers got slammed against the ceiling. So the question was why? 2020 had a whole episode on it, I don't know, like almost 15, 20 years.
You're about to see incredible footage of what some call a white-knuckle flight. Anybody whose plane has been rocked by powerful winds knows what that means. But sometimes the air currents
Okay, guys, just watch this and then go take a break.
can be so sudden and so violent that things and people fly around the cabin, and travelers fear the worst. How dangerous is clear air turbulence? Can you protect yourself? I think the life-saving information I heard from people who've survived this terrifying ordeal is worth passing on again.
It's a moment every air traveler dreads. A jetliner tossed around like a toy in high winds. You know the feeling in midair. Now watch it from the ground in this rare video. Struggling against the fierce gusts, the pilot aborts a risky landing in California by going to full power. A close call. The passengers who've been through it, like Kenny Vance and his friends 2 years ago, usually assume the worst.
I knew that we were going to just fall out of the sky and we were going to crash. You know, I'm dead.
Imagine that fear holding a small baby. Tara Converse did on a flight in 1996.
I was thinking that it was over. That was, I thought we were all gone.
Ladies and gentlemen, we're sorry about this choppiness. It's quite windy here today in the mountain.
Pilots call it turbulence, but for many frequent flyers, it's another word for panic.
We'll ask everyone, including the flight attendants, to remain seated with their seatbelts fastened.
No camera has ever captured the actual moment of crisis in the air, but the movie Turbulence came close last year. In Hollywood, the effect was created with a giant rotating set. In real life, there is no giant safety net. A passenger did videotape these scenes of fear and confusion last December, minutes after a United 747 hit severe turbulence at 31,000 feet. The plane was forced to return to Tokyo, and despite frantic efforts to start her heart, one passenger died of internal injuries. 74 others, including crew members, were injured, some seriously. How dangerous is air turbulence? Can it rip a plane apart? Cause a pilot to lose control? At ground level, the experts say, turbulence called wind shear is a real hazard to aircraft. But sophisticated instruments on runways can detect wind shear and alert pilots to the danger. That's less true at high altitude, where commercial airliners encounter turbulence most often. Here, violent winds of different speeds and temperatures lurk in the atmosphere and prey on unwary flyers.
Stand right by your side when the going gets up.
Kenny Vance is lead singer with the Planetones. He and two of his musical partners, Murray Weinstock on keyboard and Gary Bonner, were returning to New York from a performance in L.A. Their flight ordeal began on a clear day high over Colorado.
We hit what seemed to me like a rogue wave in the middle of the ocean. It's like a huge wave, and the plane shot up in the air at this angle. Up, just straight up in the air. And I flew out of the seat, and you could see all of the other people that were also flying out of the seat. As soon as it reached the high point, it started to drop. And at that point, the stewardess was on the floor, was boom, thrown to the ceiling.
So was Jake Converse aboard a different flight. Tara was feeding a baby yogurt.
And Jake went flying out of my arms, and yogurt went all over the place. And he hit it. The reading light broke with his head.
Restrained by her own seatbelt, Tara watched helplessly as the infant lay prostrate against the overhead luggage bin.
I remember looking up, and his back was just flat against the top.
Was he hurt at all?
He had on the side of his head, it was red, and where he had hit. And I kind of held him real close to me and tight after that until we landed.
Jake was lucky. Both planes eventually landed safely, but ambulances lined the tarmac. More than 20 passengers were carried off on stretchers, many with head and back injuries.
This flight we landed, we're safe.
Turbulence is the leading cause of in-flight injuries. Every year, more than 50 passengers are seriously hurt, usually because they've ignored warnings to buckle up in storm-related turbulence.
Clear for takeoff, 115,000 feet.
I recently took a simulated flight on a 757 and experienced firsthand how commercial pilots handle turbulence on the flight deck.
130. V1. Rotate. Positive brake. You're up. You're up.
Senior American Airlines Captain Warren Vanderberg, who trains other pilots, was at the controls. We took off from Vail, Colorado, and climbed toward the Rocky Mountains, a region notorious for bumpy air rides.
You look out to the horizon, you see it's starting to get rougher.
Our first encounter, the fringes of a thunderstorm. Cockpit radar detects it 40 miles away.
Now, we avoid these things by a very large margin, but nonetheless, it's a disturbed air mass, so there's going to be some bumpiness as you pass through that area. Telling Denver we're going to start a right turn here to head 105 degrees.
Professional pilots avoid flying directly into storms they can see, so they're seldom dangerous. Not so a phenomenon called clear air turbulence. It's invisible, says America's chief meteorologist Warren Qualley.
Clouds you can see. Radar sees precipitation. It sees thunderstorms. Radar does not see clear air turbulence, and that's the difference.
Severe clear air turbulence is very rare. That's what the Planetones and Converses experienced. It strikes most often above mountain peaks where the winds flow like waves. Small clouds called rotors form within the motion and then quickly disappear, leaving a vicious rotating air mass. While computer models attempt to forecast clear air turbulence, pilots usually fly into it blindly. Sometimes it even occurs above flatlands or over water.
Good morning, ladies and gentlemen. Welcome aboard United Airlines Flight 1586.
Just ask United flight attendant Lisa Stream. In 1992, she was preparing the cabin for landing as the Jumbo 747 began its descent into Miami. Out of the blue, the plane suddenly dropped, and Lisa was tossed straight up.
I slid along the ceiling, and when we started to bottom out and I started falling back down to the floor, our passenger took my ankles, and he pulled me down, and we hit hard, and I kind of landed on the armrest. That's when the cart actually landed on the top of my foot.
Flight attendants are especially at risk. Lisa's injury required surgery. Doctors amputated a toe, and she was unable to fly for 2 years. Why do people and things become projectiles when a plane hits rough air? Captain Vanderberg explains it's the laws of physics.
The plane itself is still flying. It's not falling. It's flying perfectly well. The trouble is the environment it's flying in now is all going that way. And so as it heads down in that downdraft, as you might imagine, that will reduce the gravity possibly beyond zero, which would cause objects and people that are not securely strapped down to rise out of their seats.
The biggest myth is that you're falling out of the sky and that the plane is breaking up. But they are not.
American spokesman John Hotard says modern aircraft are built to survive extreme conditions.
These planes are very, very structurally sound.
Aircraft wings are designed to be flexible. In so-called stress tests, they withstand enormous strains never seen in flight. The wing finally shatters 150% beyond Boeing engineers' worst-case scenario. No modern jetliner has ever lost a wing to turbulence. And in this government test, an aircraft fuselage survives a 30-foot drop intact. But watch closely what happens to heavy objects stowed in the overheads.
People bring everything imaginable aboard an aircraft. You can have small television sets, you can have radios, you can have boom boxes, all sorts of hard objects like that could go flying around if you get really severe turbulence.
Like the sudden high winds that caught us by surprise in the cockpit.
Looks pretty clear out there, Hugh. Don't see any signs of weather. Rain showers or storm.
Onboard alarms alert us to an unsafe condition. But Vanderberg quickly takes manual control. He trains pilots not to rely too much on computer systems. He's convinced human hands are better at riding out turbulence like a surfer rides a wave.
Okay, let's get stabilized again on course.
High-tech devices to detect clear air turbulence are on the horizon. NASA will test a laser technology aboard this plane soon. But for now, there's a simple, low-tech answer to most passenger injuries.
I think everyone should wear their seatbelts all the time, especially kids. I think kids should be in car seats.
Even a mother's love can't hold that baby safe. It takes a child seat to do that.
That's the government's message, too. A message the planetones have taken to heart.
Keep your seatbelt on at all times.
In your opinion, do passengers take that advice as seriously as they ought to?
No, Hugh, they don't. They become complacent. They don't listen to the flight attendant announcements. They don't listen to the captain when he says, I'm going to leave the seatbelt sign off for your comfort, but if you're in your seat, turn it on.
If we ask you to sit down, it's not just because we want you out of the aisle, it's because there's a need for safety.
Base Lake to final for runway 18 right.
As we approached Dallas Airport, Captain Vandiver told me a secret.
When I'm a passenger, it's difficult for me to relax in turbulence, whereas when I'm at the controls, I know it's going to work out. You're flying the airplane.
Having made that admission, he turned the controls over to me.
Okay, start to clear. Start, pull back. Beautiful.
It was a relief to touch down. Of course, my encounters with turbulence had all been inside a gyrating flight simulator. We had never left the ground.
Well, I've been on planes with you. We've left the ground, and I'm here to talk about it. But okay. But you know, Hugh, very often when the captain says, and I fly so much, he says, we've turned off the seatbelt, but you're free to walk around. Shouldn't he say, only if you have to or at your own risk?
They ought to add something like that, really, because it's a fact that the seatbelt light was on when that passenger was killed in December. People ignored it, though, as he pointed out. It would be a great help if they did stress the importance of keeping it on.
Right. The reason I'm raising that question is simple. Guys, here's your elevator going down. Everything is falling with the elevator. In projectile motion, everything is moving horizontally while they're falling under the influence of gravity. If everything is falling under the influence of gravity, notice that the passengers inside the airplane should be seated up. All right, here's your passenger. This passenger is going to be seated up, just like that. All right, notice that your passenger and the airplane everything's falling at the same rate. You don't need to be buckled down. All right, so if it's projectile motion, if this is motion under the influence of gravity, you cannot possibly be getting slammed against the ceiling, right? So why then these people are getting slammed against the ceiling just like that? The reason why they're getting slammed against the ceiling is because this is not motion under the influence of gravity. Airplane is not falling because of gravity, not because it's heavier. Airplane is falling because it's being pushed down in an acceleration larger than the gravitational pull. All right, so what happens inside the airplane has nothing whatsoever to do with what happens inside the elevator. They're not even remotely related. All right, so the airplane is being pushed down by forces generated inside the air turbulence. So the acceleration of the airplane is larger than the passengers inside. Passengers are simply falling under the influence of gravity. The airplane is not falling under the influence of gravity. It's just being pushed down at an acceleration greater. All right, so how's that possible? That's something that we'll investigate. That's something to do with the way the airplanes are designed to become part of the air mass that they're flying in. If the air mass goes up, it's going to take the airplane with it, and the air mass goes down, it's going to take the plane with it. So the problem happens when the air mass that they're flying in starts to go down. It accelerates at a rate larger than the gravitational acceleration. All right, these two pilots, notice that the airplane is upside down, and these guys are doing it purposefully, so they're actually accelerating at a rate larger than the gravitational acceleration. As a result, he's able to actually pour his water in.
All children may soon need their own seats on airplanes. Right now, you don't have to buy a separate seat for children under 2. You can hold them on your lap. But the American Academy of Pediatrics and the FAA want that changed. The recommendation is for young children to be placed in child safety seats on airplanes to protect them from turbulence, which is the leading cause of non-fatal injury to aircraft passengers. The rule is expected to go into effect by the end of the year, and it certainly is a rule that's necessary.
It's going to be, a lot of people are going to be up in arms about that one, unless they can get a discount. Are they going to be?
It's got to be the way to do it, otherwise.
It only makes sense. I mean, everything else has to be restrained. Even the cart that serves food has to have wheels that lock. So
it's a good idea, but they've got to cut the price, otherwise parents are going to go bonkers.
I don't know. It's still a seat that's being held, so I don't know about that.
They haven't said anything
about that. Okay, thanks a lot.
Thank you, Doctor.